Hello everyone, welcome back to another BGCSE past paper review. Today we're reviewing a physics paper. This is a paper 1 from the year 2018. Again, before you start this examination, always remember to write your school number, your candidate number, your surname, and your initials. Even though I'm going to do a paper 1, I want you to understand that I'm going to explain some answers because there are some points and concepts that I need to explain in this paper to also help you with the content of the physics curriculum. Now, again, before I start the examination, please remember to read through the instructions carefully. And if you do not understand any of the instructions, or if you have any other queries, please clarify those with the examiner. All right, let's quickly jump into question number 1. And in question number 1, the diagram shows a reading on an ammeter. Now, it asks us here what is the reading on the ammeter. And so the first thing you need to do is to check the number of values or the values for each of the graduations. And so what you're going to do here now is to look closely and you realize that starting from 0 all the way to 10, there are 10 lines. And so therefore, each line values at 1 ampere. Again, an ammeter used to measure current and an ammeter must be connected in series within a circuit. All right, just to please to note that as well. And so therefore, if each of these graduations is actually 1, so therefore if this is halfway, is this 5, and so therefore it is 6, then therefore this must be 7. And so therefore answer must be 7 amperes. And current measured in amperes. All right, so question number 2 is an athlete completed 400 meters race in 47.6 seconds. What is her average speed during the race? And to find speed is equal to distance over time, right? So speed is equal to distance divided by time. And so therefore, the distance here is 400 meters. So 400 meters divided by time, which is 47.6. And that will give us a value of 8.4 meters per second. So that's 8.4 meters per second. All right, so answer should be 8.4 meters per second. And so therefore, C is our correct answer. For question number 3, and the question number 3 says which pair of quantities has the same units? And so let us quickly go through this. Is that acceleration is meters per second squared and speed is meters per second. So they are not the same. Power is measured in watt and work is measured in joules or Newton meter. So therefore is not the same as well. Weight and drag. A matter of fact, weight is a force, drag is a force. So those two are measured in Newton. So C will be your answer. Moment and momentum. Moment is measured in Newton meters. Okay, so it's moment of force measured in Newton meter. And moment and momentum now is measured in kilograms meters per second. All right, so now jump into the next question. Question number 4. And for question number 4, it said to get to his office from the entrance of the building, a man has to walk up 6 flights of stairs. So let's mark this down. He walks 6 flights of stairs. It said the height of each flight is 2.5 meters. So each flight is 2.5 meters. And the man has a mass of 80 kg. It said what is the approximate gain in the man's gravitational potential energy during the climb? And so what we're going to do here is to find the gravitational potential energy, which is, let me give it a quick formula right here. That's going to give, let's say, call it potential energy. So gravitational potential energy is given as mgh, which is mass times gravity times height. But before getting to that, let's calculate his height. Let's say total height. And so the man's total height will be equal to each flight of stairs is 2.5. And so he climbed up 6 flights. And so therefore, we're going to say 2.5 times 6. And that will give us 15 meters. All right, so his total height is 15 meters. So the find is gravitational potential energy. That will be equal to the mass, which is 80 kilograms. So 80 kilograms multiplied by gravity. And gravity is going to take us to be 10 multiplied by his height, which is 15. And so therefore, if I multiply all of that, you realize you get 12,000 12,000 joules of energy. All right. So answer here has to be D. All right. All right. Question number 5. For question number 5, it said a rock is taken from Earth to the moon, which row shows what happens to the mass and weight of the rock on the moon compared to the Earth. And now what you need to know about mass. Mass never changes. Mass remains the same. Okay? So if mass remains the same, then we can surely know that, hey, mass decrease is an incorrect answer. Mass increases, incorrect as well. So we're sure that A and B are out. Now, what happened to weight by carrying to the moon? Moon has a less gravity, or the gravitational force is lower. So therefore, we know that the weight must decrease. So decrease would be correct for that. A matter of fact, we don't need to look at A and B anymore. So definitely B is double wrong. All right. Now looking at C, it says stay the same and decrease. So that will be your answer right there. Right there, you know that C is our correct answer because both of these will be actually correct points. Stay the same for these correct, but increase in weight, absolutely not, because gravitational force on the moon is lower compared to the Earth. Question number 6. It's a ball moving with a velocity of 43.8 meters per second has a momentum of 6.22 kilograms meters per second. It's a what is the mass here? All right, and just to give you a quick formula for momentum, just to remind what momentum equals to. And momentum is written as this. The momentum is equal to the mass multiplied by the velocity. All right, and so if you want to find the mass, then mass going to equal to, let's say mass is now equal to the momentum multiplied by the, sorry, not even multiplied, but divided by the velocity. All right, so to find mass, it is the momentum divided by the velocity. All right, let's take this off a little bit. This is a little bit too long. All right, excellent. All right, so now let's put this in a formula. So momentum now will equal to, all of this will be equal to the momentum, which is 6.22 divided by the velocity, which is 43.8. And so this will give us a value of 0.142. And this is going to be kilograms, kilograms, right? So that's the mass right there. So our answer here has to be A. All right, good. Number 7. In question number 7, it says diagrams show the forces acting on 4 objects, A, B, C, and D. It said which of the diagram shows the object that only, this keyword here, only has a net force of 1 Newton acting downwards. So that only net force acting downwards of 1 Newton. So we're going to work out all of these diagrams to ensure that we prove our answer. And so if you look at option A, in the horizontal plane, it is 5 newtons in opposite directions. So it is same value of forces in opposite direction, which means the net force in the horizontal plane will be 0, okay? Because they will cancel out each other, in other words. Now looking at the vertical plane, now we notice that 3 is going up and 4 is going down. So if you make the difference between these two forces, you actually have 1 Newton acting downwards. So by virtue of the question, you know that actually A is the answer, right? But let's prove the others to make sure that they're incorrect for real. All right, so let's look at horizontal plane first. Yeah, 5 newtons going towards the left and 4 and 7 newtons going towards the right. So 4 plus 7 is 11 and 5 going that way. So therefore, if you minus 5 from 11, you'll have 6 newtons going this way. All right, so 6 newtons going in the horizontal plane. So you know by that already, you know that actually wrong, because they're only going 1 Newton downwards. All right, so a net force of 6 newtons will go to the right. And let's check the vertical plane now. 3 going down, 4 going up, so 1 Newton net going up. All right, so you know that actually B is wrong in every possible way. All right, let's look at option C. In option C, a total force going towards the left, which is 4 and 2, which is 6. 6 going towards the right. So in the horizontal plane in this diagram, it is 0. And look at the vertical plane, 7 newtons going upwards, 6 newtons going downwards. So the net is going upwards, and it is actually 1 Newton. All right, so 1 Newton is a net going upwards. So this is opposite to what the question is actually saying. Yeah, the 1 Newton is good, but it's not acting downwards, it's acting what? Upwards. Let's look at this one. 6 and 4 is 10, and 3 is going in opposite direction. So therefore, going towards this direction here, towards the left, going to be 7 newtons in the horizontal plane. In the vertical plane, we have 8 and 9, so therefore 1 Newton going downwards here. So 1 Newton is going downwards, which is awesome, but the difference is we have other force here of a net of 7, and it asks only. So therefore, A is the answer. All right, so A is the answer here. Right. Now let's go to question number 8. And in question number 8, now it said that which of the descriptions best describe the image formed in a concave mirror. So it's a concave mirror here when an object is placed between the focal point and the mirror. Now, point to note. Well, I go ahead and put in the lines already so to save some time. So what I'm going to tell you right here, that the first thing I need to do is to determine my 2F. So my focal point is F right here. So my 2F will be right here. I'll already measure it and mark it. So that's to save some time already. Now what I'm going to do is to make a statement right here that is very important for you to note. And this statement is that 2F is the same as C. I can say C, which is the center of curvature. Let's say C equals to 2F, just to make you understand that. So this part where I mark the X is the same as 2F, is the same thing as C. All right, and C is the center of curvature. Now, what I'm going to do here now is to go through a step right here to kind of show you how to actually draw the image-object relationship. There are actually 2 methods that we can use. I'm going to show you the 2 methods using different color lines. I could do them separately or together. It really don't matter, but I wanted to understand the step. Now, the first step that you should do, and which you must do, I'm not going to say should do, but must do, is this. You want to measure a line from the top of the object to the mirror in an horizontal plane, and which means that it must be parallel to the principal axis. That means the distance between it must be uniform. And so that's very important for you to have that. That's my very first line. That's the first line that you should always draw. Now, the second line could be either or, but the one that I prefer to draw as a second line, because again, the second line could be either or. But for me, my preferred line is always to draw from my first line. And so I'm going to take this line here, I'm going to match it up straight through F, all right, to where the other line actually meet the mirror. So that would be my second line right there, okay? Now my third line could be, again, an option based on the method that I'm using. So I'm going to use continue the red line, and I'm going to take this line now and take it from the top of the object all the way through the center of curvature, or 2F. So I'm going to put that line right here. Let me make sure I get it as best as possible. Let's call it right there. All right, it's going to be right there. Good. All right, so I put it right there. Those 2 lines now is all I need to determine where my image will form. And my image will form where the 2 lines intersect. So my image should be right here, somewhere there. All right? All right, my line may not be 100% perfect, but yeah, it should be somewhere right there. And notice the image-object relationship. The image is larger than the object, which means that the image was magnified. It is also erect, which means upright, and it's virtual because it's behind the mirror. All right, so my third line right here, it was an optional line. I did not need to draw that line. I could use a different method to get this. And so this would be method 2 without drawing this line. I could remove this line if I want. All right, let me just remove it for the time being so you don't get confused. So this third line was the optional line. So the other method I could use is to take this line here. I'm going to keep this in blue, so I'm going to go through. So what I'm going to take this now is to take it through F, and on top of the object as well. So it's going to be through F on top of the object and touching the mirror, just like that. just like so. All right, so once I've done that, now I'm going to make an horizontal line straight across from where this line actually meet the mirror and meet the second line that I drew. So notice again, the object is in the same exact place. So that's another method to do it. All right, so you only need actually 3 lines, to be honest with you. All right, 2 lines to actually see where the intersect is. The first line is very important to draw straight across. The point F is critically important. The lines must go through F, or as I mentioned, my first option was to put my line through 2F and have it like this diagonal. So notice no matter what method I use, the image formed in the same place, upright, larger than the object, and it is magnified because it is bigger, taller, so it's bigger. All right, actually, if we measure the line here, we could and measure the image here, measure the object first, and then measure the image, we can actually know the magnification. So we could divide it and see how much times bigger it is. So it'll be the image over the object will give you the magnifications. You could measure it as well, right? And also you could measure the distance behind the mirror, how far it is, and if it is the same distance as F or and so on. So you could do there are a number of things you could determine right here. But the fact that the image is magnified, upright, and virtual, then we know that C is our answer. The point to note that I want to make mention here will kind of assist you as well is that once the object is very close to the mirror, the closer the object is to the mirror, the larger the image will be, and it will also be virtual. So closer to the mirror, the image is magnified. It will be virtual, which is behind the mirror itself, and it will be so, and it also be erect. Now, if the object was beyond F, right, or far away from the mirror, as far away as possible from the mirror, so whether it be at F, between F and 2F, or beyond 2F, what will happen is that the image that is formed will be real, right? And it will also be reduced in size, so it will be diminished, which will be smaller, and it will be real, all right? And of course, in some cases, well, most of the cases, it will be also inverted, which means turns upside down, all right? I think at 2F, yeah, at 2F, it will be the same size and inverted. So that's the time, that time right there will not be diminished, but will be the same size if you have 2F. So just to make a note right there. Yeah, but once you practice drawing these lines, you should be awesome in drawing an image formed from mirror or from lens. All right, let's go to number 9. Now, for number 9, it said that the diagram shows a submarine moving in the direction shown by the arrow. So the submarine is going forward. It said what term is used for the force acting against the motion of the submarine? And so what they're actually asking you here, what is this force that goes in opposite direction, is going against the motion? And that one, we call it the drag. All right, just like the airplane question we did, I think that was in combined science, I think. Yeah, but it's a drag, right? So you need to know the forces on an airplane, the force on submarines, and so on. All right, so let's go to the next question now. Question number 10. And they say a student investigates the principle of moment by hanging 2 weights of 20 newtons and an unknown weight y from either ends of the ruler. The 20 Newton weight is on 25 centimeters, as you can see right here, from the pivot, and the unknown weight was placed here at 75 centimeters from the pivot, as you can see right here. It said the weight of the ruler is negligible. All right, so once that means the weight of the ruler is not taken in account. All right, so we're going to consider it as being negligibly. All right, so here now, it said if the ruler is in equilibrium, what is the weight of y? So let's find out here what is the force y. All right, so first thing you need to know that the clockwise moment is equal to anti-clockwise moment. The 20 Newton is causing a anti-clockwise moment. Let's show you why. Because it's going to turn this way towards the pivot, so it's going to anti-clockwise direction, while y will be a clockwise moment because it's turning towards the clock, towards the pivot, or away from the pivot. So you can go like this as well if you want. So that's clockwise, and away from the pivot, this way it is anti-clockwise. So wherever you take it, 20 Newton is anti-clockwise, and the y is our clockwise. So again, the total anti-clockwise moment is equal to total clockwise moment. So what we can say here, based on this, we can say 25 centimeters multiplied by 20 newtons is equal to the moment of y, and we don't know what y is, so let's say y multiplied by 75 centimeters. All right, so we can work it out like that. Now, based on this formula, we can actually could say that let's work this out. 25 times 20, that's going to give us 500. So let's say 500. Let's say 500 equals to y times 75, right? And so to find y now, we can say y equals to 500 divided by 75. And so what you're going to get there is going to be 6.7 newtons. And so answer here has to be D. All right. All right, so we're going at that question. So question number 11 is a ball of mass 4 kilograms is dropped from a height of 15 meters to the ground. All right, so here's access now. So if the energy lost is overcoming resistance, overcoming resistance, it again is negligible. What is the approximate velocity of the ball just before it strikes the ground? All right, and so again, if no energy was lost at all, then what we're going to assume here now is that the total potential energy will be converted to total kinetic energy. But before I get to that part, let me just make a little statement right here. At the maximum height, at the very maximum, this is what we know for sure, that the potential energy, whatever the potential energy is, it must equate to mgh. That's what we know. And what we also know at this very point is that the kinetic energy, let's say kinetic energy here is equal to 0. Because at maximum height, the object is momentarily at rest, not moving at the maximum height. All right? And so at the bottom, however, at the very bottom, we know that the potential energy will equal to 0, right? Will equal to 0. But the kinetic energy here, the kinetic energy will equal to what was mgh on top. So in other words, it's going to equal to half mv squared. All right, so equal to mgh, that was the energy on top at the maximum height. So in other words, what I'm saying here is that potential energy will be totally converted to kinetic energy when it hits the ground. And when that kinetic energy is equal to half mv squared. So what we also know is that, and let's put it here, that that mgh here, that was on top, is equal to half mv squared. Let's just use it 2 as a square. Just know that is a square, okay? All right. Just know that is a square. You know what? Let me take it out and let me write it in. So it's half mv squared. All right, we know that for sure. All right, let's call it a square. Yeah. So mgh, whatever the energy up here, is equal to the energy at the bottom. So mgh must equal to half mv squared. What I'm simply saying is that the total potential energy must convert it to total kinetic energy. That's simple what I'm saying. So this turns into this at the bottom of the diagram. All right, so he asks us to find here what is the approximate velocity just as the ball hits the ground. The first we need to find what the potential energy is. So let's do that quickly first. So potential energy at the very height right here should equal to, so PE, let's say potential energy, it's equal to the mass, which is, let me go up a little bit more so you see exactly what I'm doing. So the mass is 4 kg, so we're going to say 4 multiply by gravity. Let's take gravity to be 10. Okay, so 4 multiplied by 10 multiplied by the height, which is 15 meters. And so here we're going to get a value of 600 joules. Okay, this is going to be 600 joules of energy, potential energy at maximum height. So what do we know here is that this mgh, so this mgh is going to be 600 down here. So 600 at the bottom is equivalent to half mv squared, right? So equivalent to half mv squared. Let's put in that, let me draw in that again, half mv squared. So all we need to do now is to find v. So based on working, let's just quickly put it here. I think it could hold here. All I'm going to do is to say, okay, let's find v squared first. So we can find v squared, make v squared be subject of a formula. We know what mass is, right? So half m, which is half mass, So half mass is going to be 2 because this is 4. So let me just highlight that. The mass is 4 kg. Then half the mass is 2. Okay. Half the mass is 2. All right. So the mass is 4 kg. Half of that mass is 2. All right. So let's plug that in the formula to say, okay, V square. So let's say V square. Let me put this here. So we can say that V square. All right. So V square is equal to half of mass. All right, let me take off that so you can see that properly. All right, so V squared is equal to half of mass. Let me say 600 here, divided by half of the mass. So I'm going to say here, 600 divided by half of the mass, and half of the mass is 2. Okay, so that I will have right there based on this formula. So we know that this equals to 300, right? So this is going to equal to 300. All right, so that is 300 joules here. Well, we're not even finished yet, but I just want to kind of make a note there. This is equal to 300. Now, what are you going to do to find V? We do not want to find V squared. What I want to find is V. Let me put it at the bottom here now. So I can say that V, based on that formula, is equal to the square root. All right, so V now is equal to the square root of 300. So V now is equal to the square root of 300. And so this now should equal to the square root of 300 is giving us 17 point, what I get here, 32? Yeah, 17.32. All right, so that's based on calculation there. All right, but the answer here says they say 17, so that is, and it's approximate, so it could be a little bit more or less. All right, mine's a little bit more, which is 3.2. And so, yeah, C is our correct answer. Again, so what you need to understand is that the potential energy will convert to kinetic energy. And so at the top of the highest point is as potential energy, no kinetic energy, but at its fall, the potential energy converted to kinetic energy. All right, especially if no energy was lost. All right, question number 12. Question number 12, now say diagram shows a simplified drawing of a refrigerator. All right, and so it's a which change of state is occurring at X. So what is taking place at X? Again, X is what they call a condenser. That's the first thing you need to know. So X is a condenser. So it's a condenser. And a condenser here is actually what is used to condense vapor into liquid, right? So it's condensation taking place at X. So the condenser means this condensation taking place. All right, so condensation taking place. So what I want to understand is the liquid will, the gas will convert to a liquid. So inside the freezer component, you have these coils, and we call these the evaporator. So the coils within the freezer, it is evaporator. Now, what evaporator does, if you think about it, just like when you're sweating, when you sweat and the water evaporates from your skin, it actually takes away heat from your skin. So sweating, when the sweat evaporates, it actually cools your skin, take away heat from your skin. The same thing happens to a freezer. The evaporator, which are these coils in the freezer, will take heat away by evaporating the gas within the tube. Okay, and so once the heat is removed by the vapor, then when it reaches the condenser, what will happen here is that the gas will convert into a liquid. And then it will travel all the way down as a liquid form. Notice here, liquid here. The liquid will be transported to the pump, and the pump will push it back up into the freezer component again. The liquid again evaporates, take away heat, and then again condense, and it keeps cycling just like that. And it will maintain your refrigerator, your fridge, remaining cool, or keep the things frozen. All right, so the answer there is just condensation, which is gas to liquid. So the change of state here is condensation. All right, so condensation is really the general principle that refrigerator is based upon. All right, and so condensation is really the loss of heat. All right, because remember when you move from gas into liquid, you have to actually remove heat from that. So that's why that's why the back of a fridge actually will be warmer than the front of your fridge. So you put your hand behind the fridge. Well, be careful. If you touch electrical components, you may get shocked. But the back of your fridge is warmer than in the front of the fridge itself, because heat will be given off at the back because of the process of condensation. Gas turned to liquid, heat is lost to the environment, right? All right, number 13. So let's travel through this a little bit faster now. Now, here in it said the diagram represents the effect of heat and cold on volume of air in balloon. Now this is cold, this is heat are getting hotter. And so notice if it moves from the balloon at normal temperature. So this here is room temperature, this is normal temperature, standard, well, not say standard, but the normal temperature exists at in room temperature. If you make it become colder, what will happen? The balloon will get smaller in size. And simple what we can say, if it gets smaller in size, there's a decrease in volume, right? Let me just make a note right there. So right here we have a decrease in volume. So in other words, if temperature goes down, what it's saying is temperature goes down, right? Then volume also goes down. That's what this is actually saying. And when you increase the temperature here now, when temperature goes up, right, because it gets hotter, it means that the volume also increases. All right. So that's the relationship that is taking place right there. From normal to colder, temperature drop, the volume also decreases. The balloon gets smaller. From normal to hotter, temperature increases, the volume also increase. All right. So if you notice, the size of a balloon increases. All right. It said, which law best explains what happens to the volume when the balloon is placed in a hot, heated room? All right, so I'm going to tell you some things that I used to use to remember these laws. And so let's start with Boyle's law. All right. So for Boyle's, he actually explained that that pressure and volume are inversely related. All right. But listen how I used to remember it. Is that boys, all right, I'm not saying boils, I'm saying boys, as in little boys. Little boys really can't take the heat at all. All right, so let me write that down. Little boys can't take the heat at all. So for Boyle's law, let's say boys can't take the heat. All right, so boys can't take the heat. All right, they really can't manage. If things get too hot, they go on. All right, so if boys can't take the heat in Boyle's law, temperature is constant. So let's say T, temperature is constant, all right? Temperature is the same or constant, all right? Temperature is constant or remains the same, all right? Again, boys cannot deal with the heat, so they don't talk about heat at all. So the only thing that boys representing boils actually talk about is that as the, let me write these in, as the pressure increases, so now there is no temperature. So if you increase pressure, think about pressure as in pressing down on things. If you squeeze on the pressure of the particles of gases, then the volume will also decrease, right? So this is what actually Boyle's saying. That increased pressure, the volume will decrease. So in other words, if you compress the gas by applying pressure, then what will take place here? The volume of it will decrease, all right? Let's take that out. That's not looking so nice. Yep. So let's put the decrease here. So in other words, that they are inversely related. As one increase, the other one decrease. Now let's talk about Charles. Now Charles, think about the word Charles. Who do you remember when you think about Charles? Royalty, right? Yeah, Prince Charles. So guess what? Prince Charles now. Prince Charles is royalty. As a matter of fact, Charles sound like a big man, right? So we're gonna say Charles. Olden days name, Charles. So Charles is a royalty. What you do not do with royalty, you don't pressure royalty. No, you don't do that. Neither do you pressure big man. No, you don't do those things. No, absolutely not. So you do not pressure. So don't pressure royalty. Don't pressure at all. No, that would be out of your place to do that. No, you never dare do that. All right? So no pressure for royalty at all. Do not pressure royalty. You just don't do that. All right? All right? You do not do that at all. All right? All right. So do not do that at all. And so here now, do not pressure royalty or man, Charles. And so again, if there's no pressure, so since there's no pressure, and put it in bracket here, no pressure at all, our pressure remain constant. So pressure is, let's say constant here. Pressure is constant. You do not apply pressure to royalty at all. I guess they do the pressuring, yeah? Or keep us down, I guess, I don't know. All right, so if there's no pressure, and you think about it, if you increase the temperature, so as temperature increases, let me write in these as well, as you apply temperature, increases the temperature, then you expect the volume, because we're only working with volume now, So volume is equal to an increase as well. All right, so increased temperature, volume increases. Decreases temperature, volume will decrease. And what I wanted to remember again when we talk about the gas laws is always the relationship of P and V and T. Again, what I want to know that T is always the denominator. T is always the denominator. Temperature is always and forever will be the denominator in end of the formula. So you can say P1 V1 is equal to P2 V2, or P1 V1 over T1 is equal to P2 V2 over T2. As again, T is always the denominator. All right, so let's look at pressure law. The pressure law, all right, and listen to this one now. This one, I do not take this out of context, right? But the pressure law is also called the Gay-Lussac law, all right? So let's just, again, do not take this out of context. I'm going to say something, but do not take it out of context at all. So it's a Gay-Lussac law as well. So it's also called that. All right. So Gay-Lussac, Lussac's law. Same thing. All right. Now, as I was explaining, right, that as you talk about, if you just go ahead and say Lussac is gay, that's not a nice thing to do. That don't hold any weight. It don't hold any volume. You can't assume that about the man. No, you don't do that. You don't assume these things about people, right? And so you cannot say is gay. Let's use gay as happy, right? All right, I don't want to offend anyone at all. But yeah, let's use the word gay as being happy. You can't just assume that somebody is happy because he's smiling at all. You can't do that. You just can't do it. All right? So a person could put on a very pleasant face or smile all the time, but you can't assume that they're actually being a happy person. So it doesn't have any volume. It doesn't have any weight. So with this now, there's no volume. Okay, no volume with this one. No weight at all. No volume. All right, and so it don't hold any space. It don't hold any space in society by saying, assuming persons demeanor or the outcome by just looking at them. No, you don't do that. And so therefore, if the volume is constant, then what we can say here now, the only relationship that exists is between temperature and pressure. And so as an increased temperature, let me just put it here, as an increased temperature, the particles will move faster, bombard more on the container, and if you have more bombardment of particles, then you also have a greater pressure as well, right? So therefore, pressure will also go up. So temperature is proportional to the pressure, as well as temperature is proportional to volume. And you need to remember what law state what. All right, these are some really information. I like to give you the excess information here to make sure you understand the concept when you go inside of the examination. So based on what is happening here, again, as temperature increases, volume increases. So therefore, Charles will be our guy in this case, right? Newton's first law of motion doesn't explain nothing that is happening to the balloon at all. So that is out of this question. All right, so just to remember your gas laws, all right? Number 14. But number 14 is which diagram shows a machine using second class lever. Again, is another opportunity for me to teach you something here again. Now, easy way to remember machines in terms of if they're first, second, or third class is to remember this thing, FLE. FLE, which is flea, right? Now, these that I put here represent fulcrum. F is fulcrum, L is load, and E is effort. And again, it's based on what is in the middle. Okay, so when you understand this now, the first one is first class, the second one is second class, the third is third class. So based on what they put in the middle, determine the class of lever. Let's just put this down for you. So this means fulcrum. So if fulcrum is in the middle, is a first class. The second letter is L. So if the load is in the middle, which means it is a second class, and if the third letter, which means effort, so it means effort in the middle. This is effort. So if effort is in the middle, then that is a third class. So follow me now. First class, fulcrum is in the middle. Second class, load is in the middle. Effort is in the middle, third class. So this is what is in the middle. That's a kind of a game you can make it up. What is in the middle? FLE. If a fulcrum is in the middle, first class. If load is in the middle, second class. If effort is in the middle, third class. First class. So that's FLE. All right, so let's look at option A first and foremost. I mean, by experience, you know that this is a second class lever, right? But think about it. Here we have our load here. Let's put it here will be our load, which is the weight of the things within the wheelbarrow. That's our load. Our fulcrum will be here, all right, and our effort will be on the handle of the wheelbarrow. So notice load is in the middle. That means it is a second class. Load is the second letter, so it's a second class lever. All right, so this will be your answer here. Looking at this, the elbow right here, let's put the letters here. This will be our load. All right, that will be our load right there. This here will be our effort. This is the muscle, is the effort. And this will be our fulcrum. So again, fulcrum is in the middle. That means it is a first class. So this is a first class lever right here. A crowbar is always a first class. Load is right here. All right. Effort is the man pulling onto the bar, and this is the fulcrum. Fulcrum is in the middle, first class. All right. This here again in the fingers here is going to be your effort. Where the scissors is turning, that is the fulcrum. And what is trying to cut will be the load. And so again, fulcrum is the middle, first class. So we have 3 first class levers and 1 second class, which is the wheelbarrow. All right, so remember what is in the middle? FLE. Fulcrum first, middle, first class. Load in the middle, second class. Effort in the middle, third class. Number 15 is which of the following is a vector quantity? And vector quantity has both size and direction. I need to remember that displacement has both size and direction because displacement is in a particular direction. So off the bat right there, we know that B is your correct answer. Others are pretty much scalar quantities. All right. 16. It's a family of 5 with a combined weight of 4,000 newtons. So the combined weight here 4,000 newtons, right? Together they apply a pressure of 20,000 Pascal on the floor. So what is the total area of contact on the floor of the elevator by the family? And so before to answer this, what I need to know first and foremost is that to find pressure is force over area. Okay, so pressure equals to force over area. Let's take that out. Is equal to force over area. And again, I want to bear with this because I want to explain points as I go along, so at least you get some knowledge on different concepts. All right, so therefore to find the area now, to make area, the simple formula is going to be force divided by the pressure. Okay, and so therefore we're going to have here the force, which is 4,000. That's 4,000 divided by 20,000. All right, and so divided by 20,000. Yeah, that is 20,000. And so all of that going to equal to 0.2, and that's going to be 0.2 meters square. Okay, so meters square. All right, so our answer here is A. All right, answer there is A. Number 17. For number 17, it's a student applies various weight to a spring and records its extension for each weight. The results are plotted on the graph shown. And so on the y-axis, we have force, and on the x-axis, we have our extension. It's which weight will cause a spring to stretch from 0.14 meters to 0.2 meters. All right, and so let's kind of mark on our graph where these will be. So let's start first. It said one. Well, let's go back to this again. I think I missed it. It said 1 point. Okay, so it says 0.14. All right, so what we're going to find is 0.14 on our graph first. So 0.14. All right, so let's look where 0.14 is. And so here, 0.14 will be right here because 0.12, so the 0.14 is here. So I'm going to come right up here. All right, so that's going to be hit right there. Let me kind of go across. And so this go across to the 7. All right, so the 7 stops there. All right, let's look at the other one, which is 2. So 2 will go, let me go up a little bit. 2 will go straight through this line, like so, and then it comes here. And so the extension that causing this change is from 7 to 10. So you can just say 7 minus 10 is going to be 3, okay? So 7 minus 10, well, 10 minus 7, I should say, or 7 from 10, you get 3 newtons. So 3 newtons will be our force that caused that change, all right? All right. Next question here now. Question number 18. Right, it says a student investigates the behavior of light in four transparent materials, A, B, C, and D. And notice here is the angle of incidence and the angle of refraction. And so let's see what it asks us here. Oh yeah, so which material has the highest optical density? So this is asking for the highest optical density, which has the highest optical density. So first and foremost, what you need to know, if object is moving from optically less dense to optically more dense, then the light will bend towards the normal. All right, let me quickly draw that exactly what I'm saying. So let's say, for example, outside here is air, and we have a glass block, for example. Let's draw a glass block. All right, and so if you have a normal like so, and then you have an incident ray going in like that, this is the angle of incidence. We can call that I. All right, and so it will bend towards the normal if this is a glass. So it bends towards the normal. And so what will happen here, if it bends towards the normal, which means the angle of refraction is smaller than the angle of incidence. And a matter of fact, the denser this object becomes, is the more this will bend. There's more bending will take place. So if it bends more, it therefore means that the angle of refraction is going to be less. And so here now, our answer here will actually be D. The same angle of incidence, but because it's more dense, then it will bend even more. All right, and what you also need to know, let me quickly do this as well, complete this diagram here. If this line should continues through the block, what will happen here again, it will create another angle of incidence, which is here. All right, and notice the relationship between Z angles. All right, so from a Z, all right, you know that the angles will be similar on opposite sides. And so what will happen here again is that it's this will kind of spread out again. So this here, which is now the angle of refraction coming out of the block, is the same thing as the incident up here. And this angle here will be the same as the angle right here. So the Z angle, remember this is a Z, so this here is going to be like R. So this again is equal to R. It's not called refractive angle though, or angle of refraction. So it's equal to R, I'm saying it's equal to R, which means the same value as R, but it's not called the same. It's actually called the incident coming out of the glass block. And this one again is equal to I on the opposite side. All right, equal to I on the opposite side. And so let me just quickly highlight now. Let me just quickly show you the Z angle here, just to kind of make sure there's a little mathematics really, for you to understand it. So the Z angle, if you think about it here, from here, what I'm doing in blue, that's a Z. And so the opposite sides, the angles are equal, all right? Just to make a note here. So you can use those simple things to kind of help you out with your finding out angles and so on, angles of incident, angle of refraction, things like that. Now, number 19, it said a performer is wearing a blue and red striped shirt on a stage. It said the lighting technician is using blue stage lights. So he's only using blue stage light. Let's make sure I like that. So the stage light here is blue. The person is wearing a blue shirt with red stripes, a blue and red stripe. So blue and red shirt. It don't matter if it's striped or whatever. The fact that it's blue and red, that's the most important thing. It said, what is the color of the blue and red striped shirt as seen by the audience? Now, what you need to know about light, right, is that whatever color the material is, it will reflect that color, okay? It will reflect that color. Whatever color is opposite, it will absorb it. So in other words, if you think about the spectrum of light, white light contains 7 colors of light. If you shine a light on a green leaf, you see the leaf has been green because it absorbed all of the colors and reflect green light. So if you think about this carefully, right? If you think about this carefully, if blue light goes onto blue, it will reflect that blue. The blue will come back out. It can't absorb that same color, right? So you're going to reflect blue. So blue will come out like that, out of the blue itself. All right. So if you put blue light onto blue, it's going to reflect the blue light. There's no other color except blue. So the fact that the stage lighting is blue, there's no other color to be absorbed. So the blue light will be totally reflected. Now, if you put that same blue light on the red, what will happen here? No light will be reflected. Why? Because the red will absorb that blue. The red absorb the blue. Remember, only blue can reflect blue, okay? So red absorb the blue light, and if there's any other color, matter of fact, the red will absorb them. So red could only reflect red. So if you notice now, if there's no light coming off the red, the absence of light equals to what? Darkness. So if there's no reflection of light, then the red will appear to be dark. The blue shirt, the blue part will appear blue, and the red will appear dark because there's no light coming from it. Wherever any object that do not reflect light is seen as black or darkness. And so we must see here blue and black. And so therefore A is our correct answer. All right, so I hope you get that picture. Whatever you're seeing is the color that is being reflected. So blue light alone, the blue shirt will reflect that. Number 20, it's a diagram shows the parts of a wave labeled A, B, C, and D. Now it said which two letters label amplitude and wavelengths respectively. All right, so let's quickly talk about them real quick and just kind of mention some things here. A, we're sure that A is the wavelength, right? Now remember what wavelength is. We talked about that before. That wavelength is really the distance between two equal consecutive points on a wave. And so this point here that I'm highlighting right here is equal to this point right here. Notice where it starts on the crest, right? Start on the crest right here, or the rising of the crest. It ends at the same point on the consecutive crest as well. So it's equal. I know usually you'll notice it comes from the middle of the crest to the next middle of the crest. It doesn't matter. Once the 2 points are equal, yes, it is a wavelength. So for example, if I put a point right here, that's the start of the wave, and it ends right here. That is also a wavelength because there are 2 equal consecutive points. That's very important for you to understand wavelength. Once the points are consecutive and they're equal points, it is a wavelength. Now, the amplitude is the highest point of a crest or the lowest point of a trough. So from the undisturbed position to the height of a crest, or from the undisturbed position to the depth of a trough, that is called the amplitude. So here is the amplitude. All right, so A and B will have to be your answer for sure. But I want to point out something here. What is C? C goes to the height of a crest, right? And also the depth of the trough. So this is actually 2 amplitude. So let's call it 2A. That is 2A, which means 2 times the amplitude. All right, so it's twice the amplitude. All right, amplitude times 2. Now what is D? Think about what is D. These only show you from the start of a crest to the end of a crest. Therefore, this is half of a cycle of a wave, half of a cycle. Because a total crest and a total trough will give you 1 complete cycle. So this is a half cycle of a wave. So this is half cycle. Again, I just want to give you some information here to kind of help you out to understand concepts. So a full cycle of wave could start from here, for example, and ends here, a trough and a crest. Or you can start from a crest, finish at the trough. That's a cycle, okay? All right, so this will be 1 wave, 2, well, this will be 2.5 waves actually here. So the whole wave is 2.5. All right, let me just quickly answer this one. So again, our answers were B and A, or A and B respectively. All right, for our answer there, let's go to the next question. Let's kind of work ourselves through this now. Number 21, it's a 2 identical stones, right, with total mass of 50 grams. So we have 50 grams here as a total mass. We're placed in 30 centimeters cube of water. So the volume of water is 30 centimeters cube. Within a measuring cylinder, the water level increased to 40. All right, so it moves from 30 to 40. So, matter of fact, you notice the line right here, 30, and then it goes up to 40. And so we know our volume of stone going to be, let's write that out real quick. Our stone volume going to be 30 minus 40, and so that's going to equal to 10. So let's say volume is equal to 10, okay? V of the stones together equals to 10 centimeters cube. All right, let's go into this now. Remember that our mass is 50 grams, right? All right, so here now it says what is the density of the stones? And so if the mass is 50 grams and the volume is 10, then the density is going to be 50 divided by 10. So going to be 50 grams over 10 centimeters cube, which equals to 5 grams per centimeters cube. So our density of the stones, actually it is C. All right, that was an easy one. And I know that you know that one easily. All right. Now, 22. For question number 22, and we're kind of pushing towards the half mark now. It says a woman is standing on the side of the road waiting for a bus to pass. The bus is 4 meters long and is traveling at a constant velocity of 6 meters per second. All right, it's a how long it takes for the bus to completely pass her. And so just some basic information here. Let's keep it right there so we can see the information here. Just some quick information here. We know that velocity is equal to distance over time, right? So V is equal to distance over time, D over T. That's what we're sure about. But we want to find time right here. So time now going to be T is going to equal to D over V. Okay. We already have our distance, which is 4 meters. Let's see, our velocity is what? 6 meters per second. So let's write that out here. So T now is equal to the distance, which is 4 meters, divided by 6 meters per second. And so that equals to 0.67. All right, and that's going to be seconds. All right. So our answer here is 0.67. That's A. All right, so A is our correct answer. All right, so let's go to the next question now. And this question number 23, it said, which motion time graph shows an object at rest? And an object at rest is very, very easy to determine based on this. I want to show you. And I know by look at the graph, you kind of see, okay, so the first one here, graph A, the distance is not changing. That means no matter how much time passed, the object is at the same place, so it's not moving. So A is our answer right off the bat. Same distance, no, regardless of time, object is not moving. So what is the other graphs then? For graph B, distance increase with time, and notice that it is directly proportional. So if distance is directly proportional to time, then that means a constant speed or constant velocity. Well, let's say distance, or let's say constant speed. So there's a constant speed right here. Same distance in terms of value chaining for the same equivalent at time is directly proportional, so it's going to be constant. Now, speed is not changing regardless of time. Also, this is a constant speed as well, because the speed is the same regardless of time. So this is a constant speed as well. I got this graph, increase in speed over time. So as time goes by, the speed is increasing. So this one here is an acceleration graph. So it is accelerating. All right. So acceleration or accelerating. All right. So A is our answer right there. Let's look at question number 24. It said an eye defect is shown in the diagram, and by virtue of where the lines intersect in front of the retina. So once image is formed in front of retina, we call that short-sightedness or nearsightedness. So that's first thing. It said which term describe the defects shown and what type of lens should be used for this correction. If the image formed behind the retina, then that means that it's going to be a long-sightedness. All right, and also short-sightedness is known as myopia, just to mention that. All right, and so short-sightedness is the answer for one. So know that A and B will be out for sure. So A and B will be out because those are showing far-sightedness. But the lens that is used to correct short-sightedness is actually a concave lens. All right, a concave lens. So C is our answer right there. Question number 25. It says diagram shows a light ray striking a plane mirror and reflecting off its surface. It said, what is the value of angle X if angle Z is 25 degrees? Now, again, some mathematical skills right here. If this is 25, because Z is 25, if this is 25, then from here to here, let me just kind of make a note right here. From here to here is 90, yeah? That's 90 degrees. So therefore means if this is 25, they're going to say 25 from 90. This gives 65. Okay, and put it here. So it's going to be 65 degrees, 65. And so if this is 65, then the angle of incidence and angle of reflection are the same. Remember that for a plane mirror, the angle of incidence equal to angle of reflection. So therefore here is also 65. And so here will be 25, right? All right, so that will be our angles right there. So the angle X is actually 65, and so D is our correct answer. All right, so D is correct for this question. All right, so we're working ourselves through. We just passed the half mark now, but again, we're going to go faster with questions that do not need to explain. I want to explain the ones that need explaining. because I really want to go in the exam and really ace this exam. Is that which vehicle has the least momentum? Least momentum. Looking for the least momentum here. All right, so it's a least momentum. All right, so let's just work this out really, really quick. So the least momentum, not the most, but the least, very important to point it out. The least momentum, if we multiply 500 by 20, because momentum is, again, mass times velocity we talked about earlier. So 500 times 20, that will give us here a value of 10,000. So it's going to be 10,000. All right, so there's going to be 10,000 there. 600 times 15, that is 9,000. That's 9,000 there. All right, let me put the comma there so you can see the values differently. And this one at the bottom here, which is C, it is going to say 2,000 times 10. That actually give you 20,000. All right, so this is going to be 20,000. And then D now, which is 5,000 times 5, that give you 25,000. That's 25,000. And so the one the least momentum here is B, which is 9,000. 9,000. All right, so B is our correct answer for that one. All right, so let's go to the next question here now. It said, which of the following is a magnetically soft material? And again, just to kind of cross out some stuff here. Aluminum will not form magnet. Also, zinc will not form magnet at all. So iron and steel, leave it iron and steel. Iron is the answer because iron, again, only form what they call temporary magnet. Steel will form permanent magnets, all right? So, and so we say steel are magnetically hard. Okay, iron is magnetically soft because they form temporary magnets. All right, question number 28. Is an inflated balloon is attached to a toy truck as shown. The mouth of the balloon is open so that the air is released. The toy truck starts to move in the opposite direction. And so, of course, here, as you know, based on the law, to every action is an equal and opposite reaction. So this will actually go in that direction there. So every action is an equal and opposite reaction. That's why this arrow is at the bottom right here, going that direction. If you turn the balloon around, then the truck will go forward, right? And so it's which law of physics illustrated by the moving of a truck. And this law, as I said, equal and opposite reaction. So every action is an equal and opposite reaction. It is actually Newton's third law of motion. And the third law of motion in the expanded form actually state that if body A acts upon body B, then body B acts up back on body A with an equal but opposite force. All right? All right, so let's go to the next question now. Question number 29. We're moving a little bit faster because these do not need much explanation than the first set of questions. It said when the voltage across a resistor is 9 volts, right? The current through it is 0.5 amperes. And I just want to point this out really quick for you because it's very important for us to understand this as well, that once you connect an ammeter in a circuit, the ammeter must be in series. Just as though this is in series, which means between two wires. And the voltmeter, which I'm put V right here, is a voltmeter. It is in parallel to the component that you're actually measuring. So voltage is measured in parallel to the component. Current is measured in series to the component. All right, so I just want you to understand that. So when you're connecting an ammeter, it must be in series. When you're connecting a voltmeter, it must be in parallel. All right, so here now it said, what is the resistance of the resistor? And just to point out quickly, a format you should remember is that V, which is voltage or potential difference, is equal to IR, okay, which is current times resistance. And so to find R is going to equal to V over I. Okay, so V divided by I. And so therefore, R is equal to V, which is 9 volts. We want to say 9 volts divided by 0.5. And any number divided by 0.5 is twice that amount. So let's say this is equal to 18. 29 is 18. All right. And it's going to be in actually ohms. All right. So it is ohms. Resistance is measured in ohms. The horseshoe sign, that is ohms. All right. Omega sign, you may call it omega as well. So our answer here has to be C. Okay. Not D because D is watt, which is power, which is different. All right. So it is 18 ohms. Number 30, it said that 200 Newton crate is pushed through a horizontal distance of 3 meters by a force of 10 newtons. All right. What is the work done? All right. So this one now is a kind of a loaded question, even though it's a simple question, because there's so many things we can find from this one simple question here. All right. But what I want to point out, the crate itself is 200 newtons, right? So I just want to kind of draw this, maybe kind of understand the visual representation a little bit better. But this is the crate, and the crate is actually 200 newtons. That's the weight of the crate is 200 newtons acting downwards, because weight acts downward. So this is going to act downward on the floor, right? So it's 200 newtons acting downwards on the floor. All right, so let's put back my little thing right here. All right, so 200 newtons acting downward. Now, if you push onto the crate, you push onto the crate with only 10 newtons horizontally, because the two forces are in two different directions, right? So the newtons here is 20 newtons, 10 newtons there. All right, and the travel across horizontally are 3 meters. So we have to understand that vertical component is different from horizontal components, right? All right, so there now, the work done is going to be 10 times 3, because it's force times distance. And so 10 times 3 is going to give you 30 joules, all right? So 30 joules will be your answer. Now, there's a next thing we can actually calculate is the work output. This actually called the work input, which is 10 times 3. The work output will be the work of the crate, or by the crate, which is 200 newtons, multiplied by distance moved, which would be 200 times 3, and that would be 600 joules. That is the work output. But the work input, that the work that is done by the 10 Newton force, I know they say by a force of 10 Newton. This is the work done by 10 Newton force, 30 joules. All right? By the crate itself, or as an output work, it would be the 200 times 3, which gives 600. And from that, you can even calculate the efficiency, which is the work output over work input. And you could do that times 100%. All right? But this would be a really efficient machine, whatever machine they are using, because to move a force of 200 with only 10 newtons, that's a really effective machine. Way over 100% effective. All right? Now, question number 31. It said for common circuits, for common circuit symbols are shown in the diagrams. A matter of fact, I missed out a word there. It's a 4 common circuit symbols are shown in the diagram. So the diagram below here. Now, let's quickly highlight what is what quickly, and then we talk about them. And so the first one is what they call the is a LDR. So the A is represent the LDR. What LDR means that it is light dependent resistor. Let me write that down for you real quick. So LDR means light dependent resistor. All right, dependent resistor. All right, so that's what LDR represents. And B, let's go to B first. B, let's call it, that's a diode. Right off the bat, that's a diode, and we know what a diode is, right? So that's a diode right there. And now C now, if you notice that the light is, well, the arrows are coming off, which represent light. So 2 lines generally represent light, right? And so we have 2 lines coming out, so it's actually emitting light. And so what you call this is LED, which is light emitting diode. So LED, and LED means light emitting diode. So this is light emitting. All right, so light emitting diode. All right, so that's what it is, a light emitting diode. I notice even the symbol inside of it, is a diode symbol, right? This one now, of course, by virtue of even not naming it yet, that is the thermistor. And a thermistor is really is a combination of 2 words, is a thermal and a resistor. So the thermal resistor. All right, so if you think about the word resistor, it comes from thermal and a resistor. So thermal resistor, what it exactly is. So the resistor, and it is operated by heat or sensitive to heat. And the way to draw this as well is to do this, is to kind of draw, as you do in resistor, a zigzag line, if you know that as well. And you could put the same line with the bend like that. That's the same symbol as that. The LDR, which is a resistor as well, you can also, instead of drawing the box shape, you could do that. And then you could put, I could circle that, and you put the arrows going in. So it could be like that as well. Just to point it out, so it could appear like that as well. All right, my line is not so pretty in terms of my zigzag line. So again, D will be your answer right here for 31. All right, so D is your correct answer. All right, so let's go to question 32 real quick. All right, for question number 32, it said the diagram shows two similar beakers, X and Y, containing different volumes of water at the same temperature as shown. The temperature and volume of water in each beaker is labeled on the diagram. So what I want to point out here is that the temperatures are the same as mentioned in the question, but what you notice different, you have different volumes, right? And so, it said which row describe the average kinetic energy of the water molecules and a comparison of the thermal energy in each beaker. So there are two keywords right here. We're looking at the kinetic energy of both of them, and we also look at the thermal energy. Now, what is kinetic energy? That's something I need to remind you of, and I think I talk about this several amount of times. That temperature is equivalent or proportional to kinetic energy, right? So as temperature goes up, all right, I think I'm jumping all the way down. Let's go back up. Yeah, I should be right here. Right, good. So what I'm saying now, as temperature goes up, the temperature is equivalent to kinetic energy. I just want to kind of mention that. So the higher the temperature is, the higher the kinetic energy. They are pretty much proportional or directly proportional. And so what I want to point out, if you increase temperature, there's an increase in kinetic energy, which means the particles move faster and so on. Now, if the temperature in both jars are the same, it therefore means that kinetic energy must be the same because temperature equivalent to kinetic energy. However, now what is different? Let me go back to that. As a matter of fact, let me just go back to this right now. Let me just kind of look at what is right, what is wrong. So we're looking at for them, it must be the same. So yeah, the kinetic energy must be the same. These two will be incorrect. It cannot be greater or less at all. It must be the same because they're the same temperature. Now, what next is this? We need to look out for another thing right here now, the thermal energy. What happened to thermal energy? What do we mean by thermal energy? Now, thermal energy is the heat energy within the substance. Now, by logics, let's think about this. Which of these will require more energy to get warmer or to reach 25 degrees Celsius? Think about it. A small amount of water or a large amount of water. The large amount of water requires less energy. Matter of fact, it absorbed more energy to reach the same temperature. Smaller volume of the same liquid requires less heat to change its temperature. So think about if you can cook, that is, and cooking something, small amount of water in a pot boils much faster than a larger pot. So it's going to take a longer time for beaker X to reach to 25 degrees Celsius. In other words, you have to absorb a lot of heat energy. Also going to take a longer time to cool as well. So it's going to take a longer time to release all that heat, even though it's at 25 degrees Celsius because you have more water molecules there. So yes, we're going to say Y is greater. So yes, B will be your answer. Y has to be greater in thermal energy. All right, so that's good for that. 33, let's look at 33 now. It said, what is the frequency of a sound wave of wavelength 10 meters and a speed of 300 meters per second? So again, to find frequency, let me just kind of write this down real quick for you again. V, which is the velocity speed, is equal to the frequency times the wavelength, which is a lambda sign, right? So if we want to find our frequency based on the formula here now going to equals to the speed divided by the wavelength. All right, so you could divide the speed by the wavelength. Here you get your frequency. So what we're going to do here now is that we're going to say speed, which is V, it is equal to, oh, wrong. Frequency, let's call it F. All right, so let's call it F, not the correct F, but yeah, let's call it F, which is our frequency. So frequency is going to be equal to our speed, which is 300, divide that by our wavelength, which is 10. And so what we're going to get here is going to be 30 hertz, okay? 30 hertz, all right? So therefore, C is our correct answer. All right, easy question that is. All right, so let's look at question number 34. It says, which wave has the shortest wavelength? All right, just a quick thing to help you out here to remember how the wavelengths are organized. All right, and these are what they call electromagnetic waves. So electromagnetic waves, they're also in a particular order. And the way I used to remember this is to saying that, write that down, is that radio my information. Let me write that down first. Radio my information. Let's use uppercase letter for each of the things. So radio my information. So information All right, so reading my information. All right, so I'll miss off something there at the end. Yeah. So reading my information verbally. And of course, radio is normally a verbal thing. So we're going to radio it verbally. All right, so verbally. Unless, which is you, unless X news, so let's say X news, unless X news, I'm missing off all my ends, unless X news here, unless X news is gibberish. So if X news is gibberish, I want to radio my information verbally. So I want to hear it verbally rather than X news. X news could be probably a newspaper, right? I just given a name, X news. So X newspaper, right? Unless X news is gibberish. So if it's gibberish, please radio my information verbally. Unless X news is gibberish. So how we doing this now? So R is radio. M is our microwave. I is our infrared. V is our visual, our visible light, and U will present our UV, which is our ultraviolet light, and then X is our X-ray, and G, which is gibberish, will be our gamma. And it moves from the longest to the shortest. So gamma, which is G, right here, which will be, I could also put, it's in a different color. We don't have time for all of that, but all right, let me just go back. Anyway, let's leave it as, yeah, it no matter. All right, let's keep it there. All of them let's go back to my blue. I don't want to change this back to red. All right, cool. All right, so as I mentioned here now, let me just highlight the different things that we can have right here. It's not going to allow me to do that. All right, let me just take that out first. Okay, I should, no, okay, that's all right. Just remember that R is radio, as radio is there, so that's no problem. It's the longest wavelength. M, which is microwaves, and microwaves will be the next in line. All right, and the I, which is infrared. V, it is visual light or visible light, and U, it is UV light, and X is X-ray, and G is for gamma ray. So the shortest wavelength right here, based on this lineup, there is no gamma ray shown here, so X-ray will take the next in line. So X-ray is the shortest right here. A matter of fact, radio waves will be the longest one. All right, so that will be your answer right there. All right, let's go into question number 35. So which is a longitudinal wave? A longitudinal wave here is a sound wave. But off the bat is a sound wave. Light, water wave, X-ray, they are transverse wave. And light and X-ray, as we mentioned earlier, those are part of the family of the electromagnetic waves. All right, so question number 36. In question number 36, the two neutral metals, metal spheres, are separated freely by a thin cotton thread. So they are suspended freely by a thin cotton thread. The two spheres are close together but not touching. That's very important. They're not touching, but they're close together. It's a positively charged rod is brought close to one of the neutral metal spheres, as shown in the diagram. It's not showing where the positive charge is, but I'm going to show you something here. That in the answer, all the positive is on the left. So in my diagram, we'll put my positive on the left. All right. So I put my positive here. Let's put my positive right here. Then if I put my positive there, what you know will happen, because remember these are neutrally charged things, the negative sign will come over this side. The negative particles will come towards the positive because opposite will attract, and this side will become positive. And so the second sphere now, the negative particles will go over towards the positive to attract to that, and the positive will repel, so it looks like that. And so if you look at the diagram carefully, you'll notice that right off the bat, right here, A is the correct answer, right? Because if you notice, it just look like that. The positive is right here. The negative will attract to the positive. The positive will repel. And notice even the lines are swinging over. And then because of this side becoming positive, the negative will attract to that side, and the positive will repel. And so everything will swing towards the left. All right. So that was a nice question right there. All right, question number 37. It said the half-life of radioactive thorium-234 is 24 days. A sample contains 8 grams of thorium-234. How many days will it take for the sample to contain 1 gram of thorium-234? All All right, so the easiest way to do this is just this, just simple this. Here we start out with 8, okay? We started with 8, so let's say we started with 8. It will break down to half, which is 4. Half of 8 is 4. Then it will break down into another half, which is 2. And then that 2 will break down to another half, which is 1. All right, that's the easy way to work this out. So what we're going to do here now is to do this. If each half-life is 24 days, so if right here is 24 days, that's the first half-life is 24, to break down in half is 24, so here is also 24, here is also 24. You don't have to go through all of this. You could just say, okay, it is how many half-lives, and just multiply the 24 by that number. This is also 24 as well. So there's 3 24s. If you notice it, so you're going to say 24 times 3, or just add up 24, 24, 24. So you can add up all of them. Or just say it is 1, 2, 3 half-lives, or 3 decays. Multiply the 24 by 3, or just add up all 3 24s, whichever one is easier for you, or which one you prefer, doesn't matter. So add up all of this again, it's 72. So 72 days. All right, it will take 72 days to move from 8 into 1. All right, and if you're interested, you cannot keep on breaking this down. If you break this down, 1 go to 0.5, and then 0.5 take another 24, then 0.5 go down into half, which is 0.25, and then 0.125, and then keep on going like that. All right, and so you can practice with that. All right, so let's go to question number 38. All right, this paper is really nice. I like this paper. It's really fun. 38. It's a radioactive tracer. All right, it's a radioactive isotope that is injected into the body to investigate the function of an organ. Which two properties best describe an isotope used as a tracer in this way? First and foremost, I must tell you this. One's going to talk about the body. Gamma is the best. Well, it's the only one you should use, because others are dangerous. Let me kind of quickly tell you why they're dangerous. Quick. Let's start with the alpha first, right? So alpha, it is, let's start at alpha. Let's put it right here. I think yeah, everything could hold here. For alpha particles, they are actually positive charge, right? So let's put alpha being positive. So alpha is positively charged, just to make a note right there. And alpha could penetrate the skin. I'm going to put this paper or skin right here. What I'm putting here is what it can penetrate. Paper or skin. It will be blocked by a paper or the skin. Okay, it cannot pass paper or skin. All right, so I'm even going to mention why this is not even used in terms of a tracer in the body. The next one is beta. So beta now, the beta ray is a negative charge. So beta is negative, and it can be blocked by a simple piece of aluminum. Okay, so this can be blocked by aluminum. All right, so aluminum can block it. Again, next one here is gamma. So let's think about what is gamma, which is our guy right now. And gamma has no charge. There's a 0 charge. And it can penetrate, well, it is blocked by lead, I should say. It's blocked by lead, so lead is blocking that. So it can penetrate paper, it could penetrate aluminum. And then the next particle I want to talk about, I just want to mention this one, which is a neutron. And there's a reason I'm mentioning this right here. I will tell you shortly. So 0 is a 0 charge as well. So it has no charge. And it can be blocked by a concrete. So this one go even further than the rest. All right. And again, that's kind of compare the penetratability of these particles. All right. So again, let's put my C right there. All right. So good. So again, in terms of all these properties, gamma is the best one, because again, if you put something that is positive charge and negative charge in the body, then it, as a tracer, looking for a tracer, not to react. So positive charge and negative charge, those are easier to react with substances, right? So you put in something that is neutrally charged in the body, it is better. It is better. And so you can trace it without it reacting with anything else, right? A 0 charge will not react to charged particles. Again, it can be blocked by lead. So first and foremost, you think about it. If it can be blocked by the skin, right, and you're tracing it outside, from outside to the inside of the body, you cannot find it because it cannot penetrate even the simple capillaries in the body. You will not find it. You don't know where it is. Again, it's dangerous because of a charge, but it's very difficult to find it within the skin if you're tracing it from the outside. The same thing with beta. The beta particles, yes, they are negatively charged. You might pick them up a little bit, but again, they can be blocked by a simple aluminum foil. The gamma now have a greater penetrating power, so you can actually go see through it, like search, like if you're scanning the body, actually will see it easier. And again, it has no charge, so definitely will not affect the organs or systems or the ions within the body. So it goes through as a neutral substance technically. All right, so it is the safest one to use. All right, so yeah, our answer here now is going to be gamma, and we have two gamma, but would it be a long half-life or a short half-life? A short half-life is better because you want to make sure that it does not stay in the body for a long period of time. Again, the half-life is good enough for you to do what you want to do, but after that, it should now start to break down. If it's a very long half-life, you're going to be in trouble. You can have that for a long period of time in the body, and of course, you know that can lead to even cancer or other problems. All right, or even mutation. All right, let's go to question 39. Again, whenever I find to give you information, I'm gonna give you. Trust me, that's how I do paper once. All right, so what is the function of the control rod in a nuclear fission? And I just want to talk about nuclear fission. The word fission actually means to split. That's what I wanted to understand. It actually means um, to split. And the purpose for that, for the control rod, is actually to absorb neutrons, to absorb them, not to slow them down, but to absorb them. I just want to point it out. Question number 40 is how many protons are in the nucleus uranium-238 with a 92 here. All right, just want to point those real quick that the 238 is the mass number, 92 is the proton number, and if you want to find well, I just said the proton number. So 92 is the proton number, all right, which determines the name of the atom. So again, the answer here is 92. Okay. If you want to find the number of neutron, you minus 92 from 238, and you get 146. So 146 is the number of neutron, not the number of protons. All right. So number of neutrons will be 146. All right. You minus 92 from 238. All right. Just remember that because mass is equal to proton plus neutron. Now, question number 41 is which list show the types of radiation in order of increasing penetration. And remember, talk about up there before on that question. I don't remember what question it is, but yeah, I think question 30 something. And question 30 something, I gave it this to remember that radio my information verbally unless X news is gibberish. So if we think about well, that's the electromagnetic wave. Now we're talking about the penetrating power. So I gave it this earlier, so I'm actually mixing up my information here. So the one I gave you about those are the electromagnetic wave, but I just gave you this one here, which is this one here. So alpha will be blocked by skin or paper, so that's the least penetrating. Aluminum can block beta, so that is second in terms of high penetrating, and gamma is the most penetrating. So alpha, beta, gamma in order of increasing like that, right? So let's go back to this question again. It's kind of related. So if you notice here, alpha will be your answer. Alpha is the least penetrating, so I know it's increasing penetrating power. So alpha is your least penetrating, beta then gamma. All right, so definitely B will be your answer. All right, cool. So you actually know two things right here. Wavelength based on electromagnetic waves, and we also know about radioactive substances in terms of the penetrating power. All right, so that's two things. And don't mix them up like I just mix them up, all right? Number 42. In number 42, it says which circuit should be used to measure the resistance of a LDR. Now, you may wonder how you don't know about LDRs or how you didn't learn LDRs or how to measure resistance of LDRs in a classroom. Hey, no, don't worry. That's not the concept that is being asked right here. The concept that's being asked right now is asking you, how do you find resistance? How do you find resistance? What is resistance? Do you remember the formula? V is equal to IR. Now let's talk about V equal to IR. So to find resistance, based on the formula, V is equal to IR, V equals to IR. So therefore, we're going to make R be the subject of the formula. That means you need V and I, which is voltage and current. And that goes for any component in a circuit. Now the LDR, as I talked about earlier, this is the LDR right here. So this is the LDR. So what do we need to know? This symbol here is just a variable resistor. So we don't even need to talk about this. This is a variable resistor. The resistance can change. The resistance can change in the circuit. But we need to know when we find the current and the voltage across the LDR. Now, if you look at option A, the only thing that can be determined right here is the current, which is the ammeter. So we cannot find voltage here. This is not showing us voltage. How are we going to find voltage? It's just not shown. Now let's look at option B now to see if what is making sense or what not making sense. Now, the ammeter is connected correctly because ammeter should be in series with the LDR, which is this, is in series. So the ammeter is connected correctly. Now the voltmeter is connected incorrectly. Why? Because the voltmeter is connected in parallel, which is a good thing. It is connected in parallel, which is a good thing, but it is in parallel to the variable resistor. So and therefore means that the voltage you find here is not for the LDR, but for the variable resistor. So this will be incorrect. Now look at C, part C now. As I'm saying, this is just concepts, you just need to know concepts. So part C, or option C, the voltmeter is connected in series. Bad idea, should never happen. You cannot find voltage by connecting the voltmeter in series to a circuit. No, it doesn't work. The ammeter is connected in parallel. Absolutely not. That don't work. So these are opposite. Now for option D, if you look at it carefully, across the LDR, the voltmeter is connected in parallel, which means you're finding the voltage across the LDR. And the ammeter is connected in series in the circuit. And matter of fact, in series circuit, the current is the same throughout, right? So therefore, D is the way that you can find the resistor of the LDR. Because now you know the current, which is I, now you know the voltage, which is V, and so you can make R be the subsequent formula by dividing voltage over the current. All right. So if the voltage here was, say, 2 volts and the current was 1, then you know that the resistance would just be 2 over 1, which would be 2 ohms, right? All right. Cool. All right. So let's go to 43, and we're almost there. Here now, sir, uranium-92 decays into thorium-90 as shown in the equation. Now, what is X? What is X? Now, remember, like any chemical equation, what you started out is what you end with. And let me explain that. What you started out with is what you end with. Let me put it a different way. The total things that you're starting out with is the total things that you must end with. Reason being because the theory, the law, my fact is a law, the law of conservation of matter state that we cannot make matter, neither can we create, we can't destroy them either. We cannot create or destroy matter. We can't do it. Only thing we can do with matter is actually to make them in different forms. So if we start out with a mass number of 238 and we end up with a mass number here of 234, that means a mass number of 4 is missing, right? To add this together, notice a plus sign. So if we add 4 to 234, you get 238. What it started out with, which is in front of the arrow, must equal to the total things that you end with. Now, if you started out with 92 as a proton number, and you end up here after the arrow of 90, plus X, that means this must be 2. The proton number for X has to be 2. Which particle do you remember? The mass number is 4, and the proton number is 2. In other words, it causes a decrease of a mass number of 4 and a decrease in proton number of 2. This is our alpha particle. It is our alpha particle. Do you remember that? So here now we know that this must be an alpha particle, which is A is our answer. All right? A is the answer. All right, so let's jump to the next question now. 44, and we're almost there. Almost there. Hold tight, hold tight, hold tight. We're almost finished. Now, so which graph shows how the resistance of a thermistor changes with temperature? Now, there are 2 types of thermistor, and you don't need to know the 2 types of thermistor. You do not need to know them at all. All right. So the general one that you'll do in the basic science is really those that we call the negative coefficient or the NTC type of thermistor. And again, you don't need to know the other one. Now, the general concept here is that as the temperature increases, as T goes up, let me write that down for you. This is what you need to know for all thermistor inside of the BGCSE or basic physics, is that as temperature goes up, so as temperature goes up, all right, as temperature increases, then what happens to the resistor is that the resistor will decrease. Okay, so that's a general relationship right there. All right, so increase in temperature result into a decrease in resistor. And what you need to know about a thermistor is that a thermistor is really a device that is dependent upon temperature. Matter of fact, a slight change in temperature, it changes the resistance of the thermistor. A very quick change. And so again, they're not directly proportional. Just to make a note, they are not directly proportional because a slight change in temperature give a big change in the resistance. Small change in temperature equals to a big change in the resistance. So what we use this to do is to use changes in temperature or use it measure or detect temperature. So we can use it to detect temperature or to measure the temperature within a particular circuit or component. All right, so the only graph that is showing you an inverse relationship right here is actually graph A. Because if you notice here, as temperature increases, the resistance will decrease. This is absolutely out of the picture because resistance will not remain the same. It's affected by temperature. C is a square value, which means that as you increase temperature, the resistance will increase by a squared value. It is not true. And of course, for this one now, it will be an increase, then eventually decrease. So absolutely not. All right, so A is the guaranteed answer there. All right, and so for question number 45, it says particles are emitted by a heated cathode in a cathode ray tube. It said, what are these particles called? And without even talking and guessing and even mentioning anything, electrons are the particles that will move throughout the cathode ray tube. All right, our next point right here now is at 46. It said, which row in the table is true about current and voltage in secondary coil in a step-down transformer compared to the primary? Now, here the big thing. This is saying that step down, that's it, you know, step down, which means it decreases the voltage. Bottom line, a step-down transformer mean a decline in voltage. That and a secondary mean what you get at the output, right? So the input versus output. So the output coil is a result of the affecting transformer. So that means voltage must decrease. Step down, decrease in voltage. I mean, it decreases voltage to a lower voltage. That's what it means. Now, what you need to know about transformers, though, is that power remains the same. Power in a transformer, whether the primary or secondary, remains the same. So what I'm going to put right here is that P equals to IV, which is power. Power is equal to voltage times current, or current times voltage, whichever way you want to look at it. All right, so P, which is the relationship between I and V, remain the same. So whatever you do to I and V, they will be the exact same thing. So firstly, let's look at the answers now, or the options. All right, again, for step down, we say that voltage must decrease. So looking at option A is that we say increase in voltage. That means this one here is not correct at all. This can't be the correct answer. All right, this is also not correct because we say voltage decrease. So these two are correct. All right, so far. But what you need to understand now, if you're going to maintain the same power, if you decrease the voltage, you must increase the current to have the same value. Okay, you must have the same value. That's what. If you use an example, I could use an example. I'm going to show you an example. So that means C is going to be your answer because if you decrease the voltage, that means you must increase the current to compensate for the same power. That means this must be true. Let me show you a quick thing. I know I've here a little bit of a while. So let's say, for example, if I have 2 as my current and I multiply by 3 as my voltage, right? I just want to show you this. What I get there is 6, right? So if I change my voltage, I'm gonna decrease my voltage to 2. All right, so I'm gonna skip a line right there. So I'm gonna decrease my voltage to 2. No, let's say decrease it to 1.5. If I decrease that to 1.5, then what must my current be? Should my current be the same? Should it be increasing or decreasing? 2 times 3 is 6, right? So what should I do with 1.5 as a voltage to make it become 6? I must multiply by 4, right? So here it tells you that my current must increase as my voltage do what? Decrease. So notice the values right here, right? So if I is a current, V is a voltage, For me to get the same power, if I decrease my voltage, I must increase my current. As simple as that. And a step-up transformer works differently. Step-up transformer means the voltage increase and the current will decrease, all right? Because the power must be the same. All right, let's go to question number 47. Again, just give you some good concepts here. I just want you to understand these principles. So, I mean, this is almost touching almost different parts of the syllabus if you realize that. So it's a good way to go through multiple choice for you to understand and to have these concepts down pat. 47. It's a plastic rod acquires a positive charge after rubbing it with dry cloth. It's a how did the rod acquire this positive charge? It's very, very simple off the bat. To get positive, you must lose electrons. Electrons are negative charge. So lose negative things, you become more positive. All right? So if you use a thief, stop thieving, you become a good citizen. Simple as that. You lose negative things, you're gaining positive things. As simple as that. Dropping negative attitudes, yeah, you become a more positive and enlightened person. So stop being negative. All right? That's simple as that. Don't be negative at all. Yeah. All right, now 48. It said when a magnet is moved into the solenoid in the direction shown in the diagram, right? A voltage is induced and the zero center galvanometer needle moves towards the left. All right, so the magnet is going down towards that, and the galvanometer, the needle will move towards the left or deflect towards the left. It said what change can be done to move the galvanometer needle to the right. So you must do the opposite thing, because the magnetic field versus the current and the direction, they will have to change. All right, and to change that, you only need to do one simple thing. What you need to do is to flip the magnet in the opposite direction. That's all you need to do. So the magnet must be flipped in the opposite direction and move in the same direction. So it's an old magnet in one place. That means no deflection at all. Flip the poles of the magnet and move in the same direction. Yes, that will cause it to actually change the direction of the galvanometer. Let's get C. Flip the poles and go in opposite direction. Actually go to the left as well. Keep on in the same direction. Pushing the magnet pushing it north in the same direction but faster. No, going faster meaning going to flick faster to the left. That's it. All right, so let's jump on to the next question now. 49, and one more question to go after this. It's where does nuclear fusion, keyword, fusion occurs? And nuclear fusion, which means particles come together, or particles come together really to form one bigger thing. All right, and fission is when they split. So fusion is when they come together to form one big thing. Fission is when they actually split. So in an hydroelectric power plant, that would be foolishness, because hydro dealing with water, you don't have nuclear reaction taking place in an hydroelectric plant at all. It's a nuclear power plant. A nuclear power plant actually uses nuclear fission. So the plant uses fission, and a coal burning power plant, no, that's not radioactive as well. But the core of the sun is a fusion. That means the particles will come together, especially hydrogen ions, atoms, they come together to form this massive explosion and reaction. And so it will be a fusion. Now, last question, it said, which electrical device is placed on street lamps to switch them on automatically at night? And so again, if you remember devices that we talked about earlier, we talked about LDRs, we talked about light emitting devices. And so the light dependent resistor will be the one that will turn on, because again, it needs light to turn on, or the change of light will cause it to create a switch like device. All right, the light emitting diodes, those are different. Those are LEDs. Those are what actually produce light. Where they emit light, as I said, that when they get excited by current, they emit light. That's LED. The thermistor, those will only change resistance based upon high temperature. But the light dependent resistors now, they are the one that actually will work as a switch depending on if light is present or light is not present. And basic name we call these are photocells. All right. And so C is your correct answer. Again, thank you for being here. I know that I've been here for a little while, but I really want to explain these points to you. Good luck on the examination. Do well, and I will talk to you soon. Be safe.